All right, Happy New Year, everybody. It's January 1st. Let's solve the new Keynesian model. Beginning with the households. The households are actually completely unchanged. So I guess you could just skip this video. To make it interesting, I thought we could use a different utility function and kind of mix things up. So we will be using this GHH utility function, where the consumption and labor are not linearly separable. So our intratemporal utility function is going to look like this. We'll have our consumption coefficient on the outside, and we'll actually subtract the labor disutility from consumption inside of the exponential function here. Okay, and as before, we'll use this theta. Let me use a different letter because I'll try to use big theta. I'll write it with like an H inside. So this is like a capital theta, okay? And that's going to be our dispreference for labor parameter. Okay, and then as always, we'll have a budget constraint, which is just consumption and investment, and that's equal to RT KT minus 1. I'll do this timing, okay? I just want you to really understand that this timing convention is up to you. WTLT plus profits from the firm. So this is a capital pi. And we're not done yet. We also need to describe the law of motion of capital. And since I'm choosing to do the T minus 1 in current period, then I have to use T as the next one. And we'll add investment. So we have no investment adjustment here. Of course, we know we can add that phi function if we want to have an investment adjustment. But we won't, just for the sake of brevity. And the goal of the household is to choose, as always, CT, IT, KT, KT, not KT plus 1, because we have KT minus 1. We're using the minus 1 timing. And what am I missing? LT. We'll choose all of these, and we will choose these to maximize the expected at time t discounted stream of all future utility. So we'll go from s equals 0 to infinity, beta s u t plus s. Let's call this BCT for budget constraint, and let's call this LMKT. So I can just write subject to BC T plus S, LMK T plus S. So there's actually infinite of these Lagrange. Okay, in principle, we should be maximizing with respect to CT, CT plus 1, CT plus 2, CT plus 3. The key insight is that once you solve it once, you solved it for all periods. So you don't actually have to worry about all of the future ones. Okay, and you should know how to do this. So please pause video and solve for first order conditions. Okay, I hope you did. If you did, welcome back, and we can have a check together. So we write down the Lagrangian, which will just be the intratemporal utility function. Expectation at time t. Sum from s equals 0 to infinity, beta s, intratemporal utility function, ct minus capital theta, lt 1 plus sigma l, 1 plus sigma l, all wrapped around 1 minus sigma c. We do not need two multipliers because we can do the substitution trick and get rid of IT. So I'm just going to do that here. I'm going to put this IT here. So we're going to have CT plus KT minus 1 minus delta KT minus 1 minus RT KT minus 1 And yes, I just realized there should be plus s's everywhere, so I'll go back and fix that in a second. Minus pi. Okay, and then as promised, we need to add plus s everywhere. So t plus s, t plus s, t plus s, t plus s, t plus s minus 1, plus s, plus s, plus s, plus s, t plus s. Okay, so there is your Lagrangian. And now we just have to take first order conditions, plus s, which is not so hard. If you didn't get the Lagrangian, that's fine. Keep practicing. If you don't have first order conditions yet, pause it, get first order conditions, and come back. Okay, welcome back. Of course, you know, to get first order conditions, we just take the derivative. So we'll start with CT. And set it equal to 0. We just have to look for CTs. So there's a CT here, and it's wrapped in this function. So 1 minus sigma c will come down. It'll cancel. So for the interior, we'll have CT, and we're in time s equals 0, because otherwise we don't have CT. We have CT plus 1 or something. Theta LT to the 1 plus sigma L divided by 1 plus sigma L to the minus sigma c. We use the power rule, reduced by 1. Derivative of the inside is just 1, because all of this term will go to 0. CT, derivative of CT with respect to CT is just 1. And then we have a CT here at s equals 0, and so we get a minus lambda t. And is there any other CTs? There is not, so we're done. Wonderful. And right away, we can see that in the Lagrange multiplier, we're going to have LT. So here's a big difference. Remember, with the CRRA, we got that LT was equal to CT to the minus sigma c. So there was no labor inside of the shadow price of utility, but here there is. Okay. Next, we will do L with respect to L, I guess. LT. Now, once again, we have to do this chain rule because the L is inside of this exponential function. So we bring down the 1 minus sigma c, it cancels. We get the same CT minus capital theta LT 1 plus sigma L divided by 1 plus sigma L to the minus sigma c. And now we have to take the derivative of the inside. We get a minus theta, and then again power rule, 1 minus sigma L comes down and cancels, and we subtract 1. So we get LT to the sigma L. Over here, we have minus WT and it's minus lambda t, so we get plus lambda t WT, and that will equal 0. Okay, and we just double check, there's no other L's, there are no other L's, so we're done. Great. Next, we need to do one more, which is KT. And remember, we don't do IT because we only have one constraint. We substituted IT away. So we do L with respect to KT. And it's KT, not KT minus 1. We always do it with respect to the future, the next capital stock, whatever we define that to be. So the first KT is here. We're going to get a minus lambda t. This is KT minus 1. We don't care about that. But we do have one here, so we're going to get plus lambda t. No, I apologize. This is KT minus 1, so we don't have one there. So we need to go to the next period because these minus 1s will become t's. So we're going to get plus beta expectation at time t. And then this KT plus, this becomes KT plus 1. We're not worried about that. We're worried about KT. So we get 1 minus delta KT. So we get minus 1 minus delta. Oh, wait, but we have a minus sign here. So minus lambda t times minus 1 minus delta KT. So we're going to get lambda t plus 1 times 1 minus delta. And then plus RT plus 1. And this looks right. And that all equals 0. Yep, this looks right. So, next, we can solve for the supply function for labor. Okay, so again, pause video and have it go. Oops, don't want this. Okay, so we need to get the supply curve for labor. So have a look and come back when you got it. Welcome back. I hope you have it. To get the supply curve, we just need to set the first order conditions for capital and labor to be equal by using the fact that they can both be solved in lambda t. So let's just plug lambda t, this lambda t, let's just plug it in right here. So we'll get minus ct minus lt 1 plus sigma l over 1 plus sigma l to the minus sigma l, capital theta lt to the sigma l, plus ct minus capital theta lt to the 1 plus sigma l divided by 1 plus sigma l to the minus sigma c, wt equals 0. And you can see right away that this and this cancels. So all of that goes away. We're left with a minus sign here and a wt here. So what we get is minus theta lt sigma l plus wt equals 0. Yeah, so we can just solve for lt sigma l. So we get lt sigma l is equal to wt divided by theta. And this is the supply curve. So what can we say? Well, normally we have CT here, so there's no CT here at all. So when thinking about how much labor to supply, the household doesn't consider their consumption at all. They just consider the wage. And they're going to scale the wage by their distaste for working. So again, remember, if the wage is 5 and they have a big theta of 2, then they're going to their perceived wage is only going to be half of what the actual posted wage is. So the higher is this disutility component, the more that firms are going to need to bribe the workers to come in. So there's your conclusion. Looking at the Wikipedia page, there was a comment about wealth effect. I don't remember. Anyway. Yes, it says the marginal rate of substitution is independent of consumption. Okay, so that's what we showed right here. There's no consumption. And depends only on the real wage. There's the real wage. Remember, we did Walras's law, so WT is real. Therefore, there is no wealth effect on the labor supply. So that's a nice thing to note. That if they're consuming, so the wealth effect comes in because when consumption is higher, then wages need to be higher to get the person to come to work. They have more money, so they don't want to work because you're already doing well, right? But in this utility function, we do not see that. That you pay the workers more, they'll work more. They don't care about what is their well-being as measured by consumption when they make their decision to work. So the last thing we have to do is just to get the Euler equation. So please pause and do that. You're going to use this, and you're going to use this. Use this, and then substitute in this, right? Use the definition of lambda t and solve for the Euler equation. Okay, welcome back. So we know that lambda t is equal to ct minus theta lt 1 plus sigma c divided by 1 plus sigma, I'm sorry, this is sigma l, 1 plus sigma l, 1 plus sigma l, all to the minus sigma l. This is lambda. And so with that in mind, let's rearrange this equation to put the lambdas together. So we get lambda t divided by lambda t plus 1, and we'll put that all in expectation because that's correct. And that will be equal to beta expectation of 1 minus delta plus RT plus 1. Okay, and you're done. You can now substitute in lambda t. Of course, I mean, written like this, it's very clear what you mean, but I'll do it. So we can plug this in. We'll plug in that the expectation at time t of ct minus capital theta lt divided by 1 plus sigma l to the 1 plus sigma l divided by ct plus 1 minus capital theta lt plus 1 divided by 1 plus sigma l. And then all of this together will be raised to the minus sigma c is equal to beta expectation at time t of 1 minus delta plus rt plus 1. So what can we say here? That when thinking about the trade-off between consumption today and consumption tomorrow, the household is also taking into account how much they're working. Previously, on this left-hand side, we only saw CT and CT plus 1. So I'm focusing here. This side is precisely the same. Okay, so this is exactly the same. This is the value of deferring 1 unit of consumption to tomorrow. So yes, this is the cost of deferring 1 unit of consumption to tomorrow. And now on the left-hand side, instead of just looking at the ratio of consumption today and consumption yesterday, we also have to look at the ratio of consumption today and consumption yesterday weighted by the amount of work that the household had to do to get that unit of consumption. So to some extent, this leisure consumption trade-off appears inside of the intertemporal consumption decision. So quite a different outcome, but hopefully just by looking at these equations and comparing it to the base case that you're becoming more and more familiar with, you can kind of make that sort of comparative analysis. And then, of course, to see how this affects the dynamical system, we would have to solve the whole model and then plug it into dynar or gecon, whatever, and then run the IRFs and sort of do a comparison. So that's the household. Nothing has changed for the new Keynesian model. We changed the utility function just to have something exciting to do in this video. In the next video, we'll turn our attention to the firm, where all of the action is going to happen in the new Keynesian model. So I'll see you there.